Okay, so we are going to do today some definition related to. Okay, so we are going to start by giving the definition of a metric space. We are going to do some examples, and we are going to move to norm space and give also some examples and do some exercises. So metric spaces, of course, we are going to start by metric spaces. And the first thing is to know the definition of what we mean by a metric space. Let x, if we take x, let x be a non-empty set. So this means that x has at least one element. We are going to define a metric because we know that a metric space is a couple of a set x endowed with a matrix. So a metric or a distance on x is a function g from x times x to r with the following property. What is the first property of distance? The first is that you have to ensure that the distance is always positive. So it means that for all x and y that you take in x, the distance between x and y is always positive. And that is what we call the non-negativity. B, if the distance of x, the distance from x, dxy equal to 0, this is equivalent to say that x equal to y for all x and y in x. The distance is symmetric, so the distance between x and y is still the distance between y and x. And the last one is the triangle inequality. So the distance between x and y is less than the distance between x and z plus the distance between z and y for all x, y, z in x. So that is a definition of a metric or a distance. Now, what is a metric space? A metric space. A metric space is the pair or the couple XG, where X is a non-empty set and G is a metric on X. So if you're asked to give a definition of a metric space, you have to give the definition and you also have to mention what is a distance. Because you can ask what is a metric space, you are going to say that it's a pair xg where x is a non-empty set and g is a metric on x. Now you have also to give the definition of what it mean by a matrix on X. So I hope that everything is clear with this definition.
Yes.
Now, example. For all X in R, so the absolute value between X and so the absolute value of X minus Y is a distance on R. So this is very easy and we can show it if you don't know it very well. So I hope that you know that the absolute value is a distance on R. And if you take y and x and y on C, so the set of complex number, this in the modulus is also a distance. So the only difference is that x and y will be now complex numbers. So x and y we have real part and imaginary part. We can prove it. So for all x and y in R, the absolute value is always greater or equal to 0, right? This is always positive.
Yes.
Then the distance between x and y is positive. We also know that the absolute value of x minus y is also equal to the absolute value of y minus x. So the absolute value is symmetric. Then the distance between x and y is also equal to the distance between y and x. If you assume that the distance between x and y equal to 0, what does this mean? It means that the absolute value between x, the absolute value of x minus y is equal to 0. If the absolute value of x minus y is equal to 0, we know that the absolute value of a number is equal to 0 if that number is equal to 0. So it means that what is inside the absolute value is equal to 0. So x minus y equal to 0. If x minus y equal to 0, this means that x equal to y. And the last one, if you have the absolute value of x minus y is equal to the absolute value of x minus z plus z minus y. I hope that you understand. So I added z and I remove also z. Now, by applying the triangle inequality, this is less than what? Absolute value of x minus z plus the absolute value of z minus y. So what do we have in the left hand side? The absolute value of x minus z, which is what? The distance between x and y. And here on the right hand side, we have the absolute value of x minus z, which is the distance between x and z plus the distance between z and y. Then we have shown the three property. So g xy equal to x minus y is a distance on R. So RG is a metric space, right? I hope that is good for you. Or you have any question, you can ask. I hope that we are together.
Yes.
Everything's okay, right?
Yes, yes.
It's like you're not alone. Okay, doesn't matter. Okay. Now we can do another one. We can take another exercise. Exercise, let xg be a metric space. Prove that for all x, y, z in x, the whole the absolute value of the distance between x and y minus the distance between x and z is less than the distance between y and z. Have you seen this kind of exercise? Or is it your first time to see this?
No.
So I hope that maybe you know how to prove it. So the hint is to use just the triangle inequality. So what do we know? We know that by the triangle inequality, the distance between x and y is less than the distance between x and z plus the distance between z and y, right?
Yes.
Okay. I can also say that the distance between x and z is less than the distance between x and y plus the distance between y and z. I'm going to see if with these two triangle inequalities, I can have this result. Now, if I take the first one from 1, I have that the distance between x and z minus the distance between is less than the distance between z and y. That is what I have. So from 2, I have the distance between x and z minus the distance between x and y, which is less than the distance between y and z. Here, if we put minus in factor, we have the distance between x and y minus the distance between x and z less than the distance between y and z. So this means what? If we multiply everywhere by -1, we are going to have minus the distance between y and z is less than the distance between x and y minus the distance between x and z. That is what we have. So we are going to take this one and this one. So if we take them together, so we have minus dy z less than dxy minus dxz. And this is also less than what? From 1. Oh, sorry. I was supposed to take this one. From 1, dxy minus dxz is less than zyz. And we conclude that the absolute value of dxy minus dxz is less than dyz. Why? This comes from the fact that we know that if we have a positive and the absolute value of x less than a, this is equivalent to x is between minus a and a. And that is what we had exactly here. This is our minus a, it is a, and this is x. So it means that the absolute value of x is less than a, as we can see. If you have any question, you are free to ask. If you have misunderstood something, you can say it. Because this kind of exercise, you can have it during the midterm. I don't know if you have any preoccupation related to metric spaces, or if you have maybe a particular exercise that you would like to solve. Do you have any exercise related to metric spaces?
Exercise my notes.
Well, so you have T in the beginning. You have a metric space. Now you have T from X to R such that if you take an element is small x in capital X, you have d ax, so the distance between x and a. So this means that your tx is what? Is dxa. Now, we want to prove that c is continuous on x. To show that t is continuous on x, we have to show that t is continuous on every point in x. So that is why we have to take a random point in x. So any point in x. Let x naught in x, and let us show that t is continuous in x naught. So if we show that t is continuous in x naught, it means that we have shown that t is continuous on x, because x naught is any point in x. It's in a particular point. Now, you have to know the definition of continuity. So we can record t is continuous in x naught if and only if for all epsilon you can find alpha positive such that for all x in x, the distance between x and x naught is less than alpha, imply that the distance between tx and tx naught is less than epsilon. So t is tx belongs to R, so yeah, t is in R. That is why the distance here is the absolute value. So the goal is to find alpha such that for all x that we take in x, the distance between x and x naught is less than alpha. Now, what do we have? Tx minus t naught is what? You have to replace tx is the distance between x and a, and t naught is the distance between t naught to t of x naught and a. And this one is how this is a property that we know. G is less than the distance between x and x naught. And don't forget that this quantity should be less than epsilon. Tx, the absolute value of tx minus tx naught should less than epsilon. So this is less than epsilon. And if this is less than epsilon, it means that g x naught is less than epsilon. And to show that t was continuous in n, we were supposed to find alpha positive such that the distance between x and L and x naught is less than alpha. And we have here the distance between x and x naught is less than epsilon. So it means that to have the distance between x and x naught less than alpha, we can just choose our alpha like epsilon. So choose alpha equal to epsilon. It means that you are going to have now the distance between x naught less than alpha because we have chosen alpha like epsilon. So alpha equal to epsilon. And when you found this alpha, it means that we are done. That was all. Then T is continuous in x naught, which is any x in x. So T is continuous on x. I hope that it is clear. Yeah, you have so you have time to watch it, maybe more time. That's one. Is there another one? Is there another exercise? I can't hear you. My headset is not connected. I don't understand why. When you are speaking, it's too slow. Just speak louder. All right. I don't know why. Just speak louder.
Can you hear me?
Yeah, now it's nice.
I'm shouting.
Yeah, you have to shout, please.
Yes, I'm stressing my notes. I said, can you use? I was saying I'm coming, but can you use exercises for your notes?
No, I don't have it now. Maybe next time. I don't know where I'm going to.
But I snapped one and sent to you on WhatsApp. Have you seen that one?
Let me check. No, you didn't send me anything.